Is that better? Okay. So, just saying, I'm not going to finish the rest of the slides before. There's a bit more technical details. We've already covered enough technical details as is. So instead, what I'm going to do is just show a little bit of the first script, so you get a sense for how we can fit a bit more complicated model. So you can see how we expand and add on to a model. So in the same way we talked about how you could have like your model where we had just had depth as a predictor. We're essentially saying, okay, we're predicting mean temperature as a function of depth. Well, we could also say predict temperature as a function of year. You might want to know, okay, is temperature changing over time in this ecosystem at a given depth? I mean, this data is actually good for this because this trawl data actually could be show you what the plot looks like. Fingers crossed this works. There we go. So it's got a pretty comprehensive coverage, and give you a sense of sort of the yearly variability. Just show you what this looks like on a year-to-year basis. So this is random stratified design, so we're sampling pretty similar areas across the whole time. This is the whole coast of Newfoundland and Labrador, or partway up Labrador. So this probably spans something like 1,000 kilometers vertically. And you'll notice they're sampling the same points pretty consistently from one year to the next. So if we want to try and model, say, both the effective temperature and depth, we don't have to worry about our depth samples varying from one year to the next. We're not like sampling only shallow water here and only deep water here. So in this case, we can try and make a prediction of how is temperature changing conditional on the depth of a given location. And in the same way with a standard linear model, you can add in more coefficients. You can add in more smooth terms with the GAN. So here I'm getting depth, just hitting depth equals k equals 20. We can go up above to see that, okay, we can actually justify setting a somewhat higher number of basis functions for depth in this case. And here I'm just fitting year, so I'm just using the default k equals 10. Again, I'm fitting this with Remel. And we can just take a look at, this will only take a second to fit. We can take a look at what the summary table looks like here. So you'll notice you still have your intercept. So it's estimating this is basically the average intercept. So averaged across years, averaged across depths, all the depths that are observed. It's estimating the average temperature is about 2.2 degrees. And then we're getting the smooths for depth and year. So you notice both of these are significant. We're looking at an overall deviance explained of 78.8%. And we can plot this. So we just plot, what do I call this? Model temp year. So we plot it like this. Actually, I have to set back to one plot. Yeah, so we plotted. The default option for MGCD is actually it'll give you each plot in turn. You have to press enter to step through them. So this is showing the plot for depth, and the interpretation of this is, at a given year, so at a specific year, there'd be this, this would be how much this would differ from the mean for that year in temperature at a given depth. So say for a given year, you happen to have a mean of, there's 2.2 degrees. This would be saying that, okay, at depths of 100 meters, so 10 to the 2, you'd be predicting a temperature that's about 2.5 degrees below that. So we'd be predicting at this point, we're actually predicting about close to 0 degrees for a year that is a mean of 0. Or here, for instance, around this, like up around say 1,000 meters, it's actually predicting a temperature close to about 1.5, 1.6, which is consistent. You actually expect this bottom water to be very close to 4 degrees Celsius, because 4 degrees Celsius is the densest water. So the water is reached the densest at that 4 degrees Celsius point, because water physics is strange. So the bottom of the ocean will typically be almost everywhere at a very homogeneous temperature. So if you go deep enough, the ocean will be very close to this 4 degree level everywhere. So it's useful to sort of think about how to interpret this. If we want to figure out what the temperature is for a given depth, it's going to be the depth at that specific point plus the intercept. So we have to add the functions together. This is just like a straight line function. This is a function for depth. If I press enter to see the next plot, then I can see variation from one year to the next. So this is showing sort of like the variability in years. So it's saying, okay, the temperature is a little bit above average around, say, 2011, a little bit below average around, say, 2006, but we haven't seen huge variation. So part of this is a lot of this area is pretty deep, and there's a cold stream of water that goes right down by Labrador that keeps this ecosystem relatively consistent. And these kind of swings in bottom temperature are actually pretty substantial. So this level of warming, this less than 1 degree of warming, for creatures that live at the bottom of the ocean is actually a pretty substantial jump. So this this point around this area is actually where we started to see cod starting to come back. So we saw some evidence of cod returning to the system around this peak temperature. But that should give you some sense of how to interpret this. If you want to think about, okay, what's the temperature in a given location, it would be the intercept plus the depth in that location, the function of the depth in that location, plus the function of the year. So you're adding them together. That's where this generalized additive model comes from. Other useful things is you can actually set so if you set pages equal to 1, it'll just plot everything in one go. So you can just very easily see both your smooth terms here. And you'll also notice that these have very different scales. So these actually have the same scaling terms here. So notice that there's much more variation in temperature with depth than there is in temperature with year. So temperature varies much less in average from year to year than it does from, say, 100 meters to 1,000 meters. Now, it can be sometimes hard to see those small effects. So what you can do is you can set scale equal 1. No, scale equal 0. There we go. And it rescales things so that each of these now range sort of between their minimum and maximum. So if you want to get a sense for how much temperature is varying without having to squint at a plot, this is a nice way of doing it. So you can see, okay, now we actually get a sense of how much variability there is from year to year. See, there's about a 0.8 degree swing from the lowest low to the highest high. And if we wanted to if we wanted to see if there's just an overall trend for temperature, like we want to just fit a straight line trend, instead of putting S, we could just use year here. And if we look at the summary for the model, we see that, okay, there is a very slight decline in temperature that's significant, but as a linear relationship, it's not very, there's not really much going on there. It's basically saying this is almost, this would be not significant at the 0.01 level. So there's not an overall strong trend, but we did see that there's actually a pretty strong, non-linear trend. Yeah?
Would you use these differently for forecasting if you want to? Yeah,
so this you can't forecast with. Like if you want to try and predict temperature variation going ahead, GAMs are not, these nonlinear curves they're using are not good at extrapolation out far beyond the bounds. We're actually working on a paper for about 3 years now, sending emails back and forth every once in a while to remind us about it, about how do GAMs extrapolate and how we can try and constrain how they're extrapolating. But for the most part, if you try to extrapolate this is basically just going to predict a straight linear decline out past the range of the data. Oh, it's going to here is going to predict a straight linear increase. So I really don't recommend using GAMs to extrapolate far outside your data. And even if you've got data where you've got a bunch of observations and you're missing a big gap, the smoother will predict something there, but be really skeptical of that interpretation because it's really relying on just that assumption of smoothness to make that prediction. And I just want to give you a sense. The other thing I want to show you of this is what happens if we use. Is this? No. Okay, I'm just going to use the method equals null. So I can't remember the actual acronym. I think so. This is without using restricted maximum likelihood. I just want to show you sort of how it changes the plot. Oh, geez. I need the one with year as a smooth as well. Here we go. So one thing you'll notice about this is, you get noticeably more wiggly curves this way. Like this variation here didn't occur in the previous plot, like this, this jumping up and down. That's kind of an artifact of using that default GCD smoothing. It tends to undersmooth the data. So you end up getting these curves that and it's very tempting to say like, oh, there must be something biologically interesting happening here, but really that's pretty much noise. Like you wouldn't be able to use that little bump here to predict something about the biology. It's really just overfitting variation. So this is why REML generally gives a much better performance in terms of not predicting too much out of sample, or not overfitting out of sample. So I think that was the major one. Oh yeah, I guess the other one, it is useful to see how we fit a random effect. So here what I've done is, so for MGCD to be able to fit random effects, you have to give it factors. The data has to be encoded to factor. You can't give it a character vector. You can't give it a number. You have to give it with LME4, for instance, if you give it you tell it inside of your random effect term, you say, oh, ID equals this and it happens to be numeric. LME4 will just happily convert that to a factor for you. MGCD, you have to do it explicitly. So that's what I'm doing. That's all I'm doing here is just turning year into a discrete factor. And then what I'm doing in this case, so now I'm fitting a model where I'm letting the year-to-year variation be modeled by a random effect. What this is doing is essentially I'm saying that I'm not putting any smoothness conditions on this. 1 year to the next could be just as big of a difference as I want or as you want. There's not any we're not predicting that there's a consistent pattern or that there's a smooth pattern to it. But we are putting at least an assumption that there's a maximum amount of variation you expect to see. That the years can differ from each other arbitrarily from 1 year to the next, but there's not a single year that's going to be 1,000 times bigger than all the other years in terms of effect. And if we plot this, so because there's no natural ordering to years, is the plot for random effects just shows the QQ plot for the specific estimates. Yep.
Where you're not specifying the K.
So for random, good question. So okay, so for a random effect, the K always is the number of groups.
Yeah.
You always, so if you have so here we have I think it's 12 years or 15 years. The K always has to be 15 because there's no way to, with the thin plate spline, it's actually using that smoothness assumption to be able to reduce the number of functions we need to fit the model. With here, there's no smoothness assumption at all. You can't if you know the value for, if someone magically told you how much higher the temperature on average was for 2005, this model is saying that it won't tell you anything at all about the average value for 2006. So you kind of have to have a single coefficient for each separate group level.
So it doesn't matter if you specify it or not. You know that
it's always going to be set to number of groups. Yeah, it's a great question. You will notice though that it's still, if I look at the summary for this, it's still setting the effective degrees of freedom to less than the number of total basis functions. So this is that assuming that random effects has some variance. This is saying that the variance is not infinite. That the years are pretty close to each other in variation, so we don't need all of the degrees of freedom that we actually have to fit that. And yeah, just to look at the plot. So then the plot for a random effect is just going to be the QQ plot for it. So it shows the predicted quantiles of the distribution and shows the estimated values for each year. So you can see that here we're actually getting, so some of these years, if the years were actually distributed following a normal distribution, if the variation from 1 year to the next was perfectly normally distributed, it would fall on this 1-to-1 line. So here what we're seeing is that, okay, the biggest year is bigger than we'd expect for under a normal distribution. So this biggest year is much warmer than we'd expect. And our coldest year is actually warmer than we expect as well. So it's actually kind of truncating, where the small values don't go that low, the big values tend to go a bit bigger.
How would you interpret this as if you're evaluating the model?
So It depends on what you need to use it for. If it's a case of like, I honestly almost never look at this plot. If it's a case of I'm just estimating this as like, as a random effect, because in that case, it's just a prior on the data. It's basically saying like, I just want them to be close to each other. I'm not willing to specify a shape of that closeness. If I was trying to make predictions though, so if I was trying to make a prediction for what the next year, how variable the next year might be, well, I might want to look at this and say, okay, I'm not using a very good, like I might actually underestimate how warm the next year might be, because I'm assuming it's normally distributed. So when I look at like the range of possible values, I might actually underestimating how warm it could be. But hopefully you're not using a random effect to predict the next year temperature, just because we do know it is warming. So it really, this assumption of normality here really matters the most when you're trying to predict something new.
So that top point would probably correspond to that. Well, it would correspond to that peak in the smoother.
Yeah, that like 2010, 2011 would be about, this is like the warmest year here. And it's, if you wanted to plot, say, year-to-year variation, you can use, so there's some code in the markdown file about how you use predict. You could actually like predict what the values are for year and just plot them versus year. So that's possible to do if you want to. It's just not the default for MGCB. That's the last thing I wanted to cover for this chunk of the first part of the lecture. I wanted to see if anyone online has any questions right now, though, or if anyone in person has any questions before we move on to the next section. Give it loads. Trying to reload this. Apologies, I think I'm overtaxing my computer's memory. It was my own fault for buying a portable computer instead of one that can actually handle running GANs. So not seeing any questions in the chat. The second part of this, we're talking a bit more about what I think are useful ideas for dealing specifically with movement data. So some of the, especially focusing on families, because like a lot of the time people aren't familiar with the different families that are available to MGCB and how they can be used to model the kind of situations you'll run into. We'll talk a little bit about interactions. I'll also talk about the issue about dealing with autocorrelation. This is probably one of the most common issues I've seen coming up in discussions with people here, is that like, if you have like a sample path that's sampled at an incredibly high frequency, and you try to fit a GAM, say, on like location of fish versus, or say temperature versus depth, your data is much less informative about that relationship than you think it is, because your data is very heavily autocorrelated. So that autocorrelation is something you have to be thinking about all the time when you're dealing with this kind of high frequency data, is that like anytime you fit a model that treats each data point as if they're statistically independent, is going to be much more confident of whatever the results are than are actually justified by the data, or by the, basically if you tried to use your model to predict new observations for say a new fish, it's going to be wrong much more often than the model will predict. And that's really the issue with autocorrelation. It's something you should be really aware of.
Okay. Question?
Yep.
So, as far as I understand, the effect size in GANs is not so straightforward.
Yeah, so the effect size in GAN, so because it's a nonlinear relationship, you really have to estimate, you have to think about effect sizes. You really have to talk about what comparison you're interested in to talk about effect size. So like just, going back to here, if we looked at, so we looked at this, we want to look at, say, the effect size, like a change in depth between 100 meters and, whatever, 10 to the 2.5, so like 70,000 or whatever meters, that's a huge effect size. Like it's almost 3 degrees. But we looked at an equivalent change between, say, log 2.5 and, say, log 3.5. There's a very small change, so
that's within a variable, right?
Yeah.
So,
if we want to compare between variables.
is there any way other than model selection to say, like, this model would work?
So you can do, I know there's functions for it, I can't remember off the top of my head, you can do like variance decomposition, so you can say, okay, this term accounts for X fraction of the variance, especially if you're dealing with Gaussian data. You could look at like the amount of variance explained by each term in the same way you would with an ANOVA. That can be useful. Generally, I think it's better to actually be explicit about what comparisons you want to make. In the sense of like, even in a linear model, I'm very skeptical of the idea that like saying that this term accounts for 70% of the variance and this term accounts for 30% is actually that useful, because it really depends on the range that you've sampled each of those variables at. Like, you know, here, if I had like 1,000 years of data or 50,000 years of data, the temperature is definitely going to vary more across year. Whereas here, I just only have a small sample of years. So I think with both linear models and GAMs, you really should be intentional about what comparisons you're making. And I think GAMs just kind of really bring that to the forefront, that you can't, there's not like an easy way to say this one is a bigger effect than the other one. Sometimes feels like the job of teaching these stats classes is always saying unpopular opinions. Telling people exactly what they don't want to hear about the models. So basically we covered some of these ideas, the idea of one-dimensional smooths. I just quickly showed models with separate predictors, so this additive models. And we looked at mostly normally distributed response data. So, and that was really kind of covering this idea of basis functions and smooths and how they can be used to predict data. The other key part about the generalized linear model, a generalized additive model, is the idea of the family. So family is a way, it's basically what we can use to capture different specialized types of data. It allows us to model different types of data. So for instance, your data might be a count. So you might have like 0, 1, 2, 3 observations. So thinking back to like Robert's talk today, if say you've got detectors that have numbers of observations of number of pings of different individuals. So that's a count, like say per day. So this detector might have had 10 pings, this detector might have had 5 pings, this detector might have had 0 pings. And if we tried to say fit a linear model of that and extrapolate, we might predict that like some detector over there is going to have -5 pings. So it doesn't make sense as a model. So counts are a special one. Survival data it's kind of specialized. It's basically modeling which individuals survive or die. But it's really important for you folks, and I think you'll cover this more tomorrow in the step selection lecture, because this is actually the basic model we use for step selection. So we use, when you're trying to determine whether an individual chooses to move through grassland, or so through seagrass or onto rocks, the model behind that, one of the most frequent ones, is essentially a model where we're treating it like a survival case, where the observed step onto seagrass is a survivor. The one that doesn't go onto grass is a mortality. We'll also talk a little bit about some of the headaches and nightmares of this high frequency movement data and some of the workarounds for it. And a little bit about adding dimensions to your smooth. And we'll be getting, I know this is called the HGAM workshop, but we'll be getting the HGAMs right at the end. So I think it is important that we kind of cover these other ideas first. And because I guess we spent a lot of time writing the HGAM paper to be as clear as possible. So typically my best advice about if you really want to learn more about HGAMs is read the HGAM paper over again. Or send me an email. But I will touch on it because I think it is an important thing to discuss. So this here, so this family.mgcv is another really useful thing to just take a scan through, because this encodes many more families than are found in the standard GLM. So you've probably heard of Poisson, you've probably heard of like normal, obviously, you've heard of binomial. MGCV has added many new distributions as well that can model more complex situations. And this really kind of walks through them. So, for instance, talk a little bit about tweeting in a second. Negative binomial is useful for count data that's over dispersed, where there's more variability around the mean than you'd expect from a Poisson. There's ones that are more complicated cases. So if you have ordered categorical data, so let's say you've done a hidden Markov model, you categorize your data into like asleep, slightly active, and a high activity. That you think is an ordered variable, like where the individuals only ever transition from, say, sleeping to low activity and then from low activity to high activity. So you can actually model like the rate of transition between these different categories using this. Basically saying, okay, like when it's warm up, we expect them to more frequently transition from sleeping to, inactive, and then from inactive to active. Beta regression. This is one that people often get excited about because it can model proportion data. So you've got data that's bounded between 0 and 1, but it's not like it's not a count, it's not A divided by B. So say it's like, say your measure is like fraction of maximum body weight or gut fullness. So let's say you've measured for a given fish how full its gut is as a ratio. So like this is, you can never put that as a count because it's a ratio of a biomass to a total volume, but it's still a proportion. And we might want to say, okay, like how does gut fullness vary in our fish by space? Scat is a handy one. Again, this is carrying on the theme of not terribly well-named functions. This one is what's called the scaled t-distribution. So if your data has the property of being similar to normal, so it can have both negative and positive, and you expect to be symmetrical around the mean, but you can have very large or very small observations, SCAT can model that. So it allows for the possibility of like outliers, basically. So I mean, this could come up a lot of time in movement data with, say, we were just talking about this yesterday. If you have like a location that, say you're measuring depth and your sensor every once in a while throws like a really bad observation, it just gives the depth as like minus 1,000 meters or plus 5 meters. But most of the time it's giving accurate depth measurements. SCAT can actually handle those rare large observations without like pulling the model towards a bad estimate. So it says, okay, this is an outlier, that's probably an outlier, I don't need to worry about trying to model that specific point. We'll talk a bit about the Cox proportional hazard one in a second. This is a really useful one. So if you ever have to deal with maxima, so if you're trying to model like whether or not, the fraction of a given population that's above a certain size class. The maximum, like these extreme value distributions are really useful for that. And this, this kind of goes on. There's like multivariate normal if you want to have multiple responses. It's kind of crazy the number of possible ways you can model this.
What do you mean by multiple responses?
Well, let's say you're trying to measure both acceleration and speed as functions of, say, location. And you think there's correlation. You think that, okay, high speed, low acceleration, and low speed, high acceleration. You'd basically have like you'd have like one set of smooths to model speed, one set of smooths to model acceleration, and then you'd assume there's a correlation between those two.
Could you model longitude and latitude as a multivariate?
You could, but maybe the assumption of like a linear correlation, because the multivariate normal is assuming that like the relationship between them is like multivariate normals. So it's basically going to be described by a straight line relationship between the error terms. So most of the time you wouldn't, if you're thinking like point processes or something, or like turn angles or something.
Yeah, we can model depth as a single dimensional spatial variable, but we can't model longitude and latitude to look at spatial area use. Yeah,
well, I think for that you need a different approach, unfortunately, because unless you just happen to have like your longitude and latitude residuals are perfectly linearly related to each other.
Like a river, maybe?
Yeah. A river that runs exactly like a river. Yeah.
Temperature and depth, maybe?
Yeah, temperature and depth could be potential.
So like the Petrol survey data you have there.
Yeah, so if you're trying to model both temperature and depth as a function of something else. So like this is like assuming correlation between the outcomes rather than the predictors. So let's say you're trying to measure temperature and depth as a function of, well, all the other things are dependent variables in there, but maybe as a function of latitude or something.
Yeah. Have you ever used it?
I don't use it frequently, but I know a lot of people who like being able to do that multivariate regression, so I try to point it out. It's not a use case I often would find, but I do know there's a lot of people, especially in the morphology world, if you're trying to do like multiple morphological measurements, you could try to measure them all at once in this kind of model.
So you can do more than two even.
Yeah, you can do arbitrarily many, it just takes a very long time to fit.
Cool.
So yeah, the classic cases, of course, are binomial, yes/no data, Poisson and gamma. These are the ones that come with it. Just give you a few examples of when it's useful. So binomial is useful for measuring, say, by behavioral states. So let's say you've got two states of awake versus sleep, and you want to determine, okay, can we predict, say, whether an individual is awake versus asleep as a function of time of day, or like the fraction of time they're awake or asleep as a function of, say, week of the year. This would be a pretty good case for binomial. Or, as you mentioned, count, so number of observations at a station, or if you are using, say, mobile sensors, you could look at, say, number of encounters with it. If this one's used all the time by people working with, say, cetacean data, where you're looking at number of whales encountered per length of transect. And then, of course, continuous. And continuous is generally broken into continuous positive only, so things like depth or acceleration, where they can't, you wouldn't expect to see, you could see a signed acceleration, but most of the time you'd say acceleration is always going to be positive or zero, or you'd say the depth is always going to be like 0 would be the lowest, and the depth would go down to, say, 5,000 meters or whatever.
So when it comes to acoustic data, so the acceleration enough and also the depth depend on the effect, they have some kind of ceiling, right? So when acceleration enough and you've got a ceiling effect, because acoustic parameters are capped at a certain value. So it's continuous to a certain point, but I still wouldn't use, like, so when you convert the data, or would you transform the data and use it as continuous, or do you use a whole different family?
So that kind of family is what's called we call it censored data, because like that maximum is a censoring effect. It's basically like we know there are observations that are bigger than that, but we can't measure them. There's not yet a good family for censored data in MGCD. I say yet because Simon Wood's probably published it. He might have already published it. That's definitely happening when I gave a workshop in the past. I think he beat me to something. But it's not currently possible in MGCD. You might want to choose how, it depends on how frequently you're hitting that cap, and how much like it matters if you only have a couple observations that are at that cap, it probably out of say 10,000, it probably doesn't matter. Like your model will still actually be able to predict accelerations higher than that. If you're hitting it quite frequently, you might want to, so BRMS, which is like a Bayesian model fitting package, has capacity to fit these sensor distributions, and you can use these smooths from it in VRMS. So if it's a case like, okay, you really need to account for that censoring, then VRMS is a really useful tool for it. It's just slower.
And
oh, sorry, it's the wrong computer. Okay. So basically the idea is that, again, we want to take a family that's appropriate for the data because it puts constraints on the shapes of functions we can get. So we're trying to predict, say, species as a function of area on the islands of the Galapagos. We don't want a curve that predicts the negative number of species. It just doesn't make sense. So here, if we use this Poisson distribution as a function of area, we can make a prediction that actually shows it appropriately. Let's run it. And it also has a nice other features that it's actually predicting the power law increase in species richness that we'd expect to see from this region. So one of the assumptions behind it, so all these families are making assumptions about the data. It's useful to be familiar with them. So for instance, the Poisson distribution assumes that the variance equals the mean, or like whatever your mean is, it assumes that the variance around that is always equal to that mean. So that bigger values have a constant variance. Typically in ecological data, we often have what's called over-dispersed data. So if this, if this curve represents, say, what we predict is where 95% of the data should lie within, you'll notice that it increases with our predicted mean for the Poisson here. These are ones where they're actually drawn from a Poisson distribution. Most of the observations lie within that interval. Here, this is over-dispersed. So most of these observations lie outside of that interval. So the residuals are either much bigger or smaller than we predict. So the Poisson often can be, it doesn't do a good job of modeling as over-dispersion. So we have a couple options for that. First is a Quasi Poisson. This is built into R. It assumes that the variance is equal to some function times the mean, so some constant times the mean. The issue though is it's very awkward to check. You can't use standard residual plots with it, or you sort of can, but it doesn't work as well because it doesn't actually have a likelihood behind it. It's got something similar to a likelihood, and it doesn't have the nice properties. It also means you can't simulate from it. So you can't simulate what new observations would look like. So in MGCB, you have the negative binomial, which actually allows you to model specifically how variable the data should be around it. And if you use this NB family, it will fit the over-dispersion term for you. If you use negbin, it won't, you have to actually specify what the over-dispersion is. And you don't really want to do that, it's not fun. So this is generally the one you want to use in these cases. So yeah, as I was saying, there's also models for categories. So OCAT is useful for ordered categorical. Multinomial is useful if you've got multiple categories and there's no natural order to it. So say you've got 5 different behavioral states and you think they could transition between any of them to any of them, or there's some probability being in any of them. Multinomial is handy for that. This is just a little bit more about the negative binomial. This is more focused for the folks working on explicit and count data, so I might skim over this. I kind of get to the families that might be a bit more interesting for folks here. So the one that you might not use as a family specifically, but is actually very useful for modeling step selections, is what's called the Cox proportional hazard model. I'm not going to go into the details of this because it's a little bit complicated, but the basic idea is you're modeling survival type data. Data that's where you're trying to model the relative probabilities of individuals who either survive or who either die. So this is basically in one of 2 categories. Yep.
For the proportion data, would we use like a count distribution with an offset, or should we use?
You mean for
like data bounded between 0 and 1?
Yeah.
Like the numerator and the denominator.
Yeah. So you can actually use. You could use like a Poisson distribution with an offset of the total sample size. It's what's called the log linear model. And you have to be careful when making predictions from it though. Like it'll actually give you the same estimates as the binomial will within the data, but when you try to make predictions, it's very easy to make predictions of like, oh, there's more observations than actual sample size. But yeah, it is possible to do it. Okay. Yeah, so this one is used specifically for step selection. So in this case, death, basically, this is modeling the probability of something transitioning state. So in this case, if you think about an individual traveling from one location to the next, the basic idea of the step selection function, which I'm going to cover tomorrow, I'm hoping, is that if you've got an individual that starts at a location, moves someplace, so this is where it ended up. So this is where it actually stepped. But we could think of there being other possible steps that it could have taken that have different characteristics. And what we want with step selection is trying to evaluate what's the probability of taking the step it did, given that it had these other options available. So given that there's, say, this area is like, if you've got a bunch of seagrass over here, and then this is all, this area is all rocky bottom, and this is in fact dry land. We want to say, okay, we want to try and evaluate, is it more likely to take a step into seagrass than it is into, say, rocky bottom or into dry land? Hopefully this will assign this, the dry land one a probability of 0. So the Cox proportional hazard model is the basic function that's used for these survival functions that lets us evaluate what's the relative preference for different habitats, given you could give an individual a set of options. So it's always about saying, okay, given that you've got these possible options to choose from, which one do you prefer the most?
Quick question, just for interest. So what's really the difference with the Cox proportional hazard to say binomial, where 1 is the step taken and 0 isn't?
So so it's actually fitting what's like in survival or in the step selection function, it's referred to as the conditional logit. Or conditional binomial or conditional logit. And it's conditional because like in a standard binomial, you're just saying, okay, you've got like some fraction of your observations are in like grassland, some fraction are in, that didn't take the step are in wetland. But it's not conditioning on the fact that like there's some steps, there's only, like for this case, you're only taking these possible steps. Like these are your only options.
Yeah.
So the conditional logic actually puts a constraint on it and says, okay, we're only going to make a comparison between ones in the same, what's called stratum. So we're basically saying we're only going to compare the probabilities of taking a step versus not for ones that are matched with each other, that are in the same group. We're not going to, so it's like we took another step here, for instance, and went over here and created again a new set of, sorry, that's the wrong one, create a new set of alternate steps. We wouldn't be we don't want to compare, say, this step with this step in our likelihood, because that is not the same set of options.
Okay, yeah, I got you.
Yeah, so that's what this, that's the survival function there. And are there actually any questions online? I realize I might have not checked this chat. So, okay. Okay. The other one that's useful that a lot of people aren't aware of is the Tweedy distribution. So this is a distribution that can explicitly model data that's continuous and positive, but has a positive number of zeros. So this occurs all the time when we're dealing with biomass data. So we're doing surveys, you put a net down, you drag it through the ocean, you might find 0 crabs or you might find 1,000 kilograms of crabs. And we need to model that case. We need a model that can account for those zeros as well. You don't want to throw the zeros out. So Tweedy can handle this. And in cases, so this might be useful for anyone who's dealing with, say, species, like you're looking for, say, distance from the bottom. If you have a species that's moving, like a benthopelagic species, sometimes moves up, most of the time spends its time on the bottom. You're measuring distance from the bottom, a lot of times it's going to be 0. But most of the time it's going to be positive, and it's never going to be negative. Like you're never going to, well, this is burrowing. You're never going to get like a Greenland halibut that has negative depth below the bottom. I know, it's biology, there definitely is burrowing ones. But it's always the problem of teaching ecology, is like every time you come to an example of a hard and fast rule, you have to immediately come up with the exception that is definitely out there. Other useful thing with the Tweedy is it has this explicit variance. So it assumes this variance relationship between the mean and the variance, like a power law. So especially when you're dealing with, say, biomass data or other similar ones, we very frequently see this kind of relationship where the variance of the distribution increases with some power law of the mean. So it's handy for that as well. That's why we use it all the time in fisheries. It's becoming very popular in fisheries because it takes that into account. These are location scale models. If you're interested in modeling both the mean and the variance of your data, so if you want to care about, okay, not only what the mean is, but how variable your data is around a given mean, location scale models can handle this. These are pretty new and are delicate. So you need to be pretty confident that you really want to answer this question, and you need to like kind of take careful steps into this world. Because like modeling both the mean and the variance of the data is very easy to get confusing models that you can't interpret. But it is very handy when you want to know, okay, is the variability of depth, say, varying? So let's say you've got an individual fish that's moving up and down in the water column. It might be that like around a given temperature, it moves up and down a lot, so it has high variance. Or around there might be another or think of, say, a measure of thermal stratification. Thermal stratification in the lake is low, a fish might be moving up and down all the time, its variance might be high. Thermal stratification is high, it might be sucked right to the thermocline, or never go above the thermocline. So that's something we might want to model explicitly, and that's what this can actually handle. Because you can't model that as a mean. Like if you can't model variability around some point as some mean, but you can model as a changing variance. Also talk briefly about these multivariate models. It is useful to know that some of these you can specify links specifically. You can actually use different links for different situations. Most of the time, you want to stick to the default link. So I'm not really going to cover the other edge cases. It's really only when you're getting to more advanced modeling that you really want to start playing around with the link function. But you can, if you want, if you've got a fitted model, you can actually access the link function if you want to do transformation. So this is actually pretty handy if you don't want to like write code to do the inverse logistic yourself because it is painful. If you go in your fitted model and go model $family $link function, this gives you your link function. This transforms your mean into your predictor level. This function will transform it gives the inverse. It takes your linear predictor and transforms it into your mean predictions. So these are just handy things to know.
The main one there would be modifying the gamma family to link log, right?
Yes. Yeah. So yeah, it's a good example of when you do actually want to modify the link. Is that the gamma distribution assumes the link is the inverse, so it's like 1 over x is the transformation, and it gets really hard to interpret your smooth terms as like, it's very easy to look at smooth terms and say that doesn't make any sense, because what it's actually reporting is the inverse of what you want, so you can just change it to using the log. And I'll show you how to do that in the code, which I think I'm getting to, yeah, actually this is a good transition point to jump over to the code. Okay. So just loading the same libraries you did before. So this is a little bit terrifying for me because this is using data I just learned about this week because I wanted to actually have a real movement data, and it's I know, is David still here? I think he was here earlier this week, right?
Yeah, but he left.
Yeah, I actually wanted to chat with him about the data, make sure I wasn't misusing it. But their group very thoughtfully provided this data online for free, very well documented under Creative Commons licensing, so I can use it here. I'm really hoping I'm not brutally misusing it. And I really hope that you folks will be patient with me as I work through these kind of complications with these data, because I think it is useful to see this with data you're used to. Yep.
Quick question, going back to the different options. That is, related to those questions, they have also models that mean of individuals being 0. Is it possible to do median or different types of?
Yeah, so there is, there's not in MGCD itself, but there's a package that expands on it that's developed by Matteo Facilio. That's called, I think it's called QQGAM, or basically it's a quantile regression version. It's using the same smoothers, it's using the same penalization framework, but it's using a different, it uses a different, not an error term, but a loss function that allows you to model. So you could actually model, like explicitly model the 95 percentile and the 5 percentile. It's really powerful, and I played around with it a bit, and it seems to be quite stable, so I would recommend if you're curious about it.
I guess I'm asking because making the median, make it more robust, perhaps. Is there another way to robustify?
So part of choosing a family, I think, is choosing one where the mean makes sense. So that's part of why we've actually switched family instead of using the normal. If you have like long tail data, you try to model the mean, it's being very unstable. But if you've got long tail data and you model it with a gamma distribution, typically you'll get a much more stable estimate of the actual mean. Because you're taking into account the fact that like when the mean is high, the variance will also be high, so it'll automatically sort of downweight those high variability samples. Yeah, so generally I would recommend paying some attention to choosing the most appropriate family for your data, because A, it's also useful to be able to make predictions going ahead. If you have a family for the data, you can actually predict what the next observations would look like, whereas you can't with the quantiles. And it also lets you, and then the other thing is to check your model and see if it's making sense. So it's what we're not covering today, but it's a really important step is to go back and make sure your model is, your assumptions of linearity are right, that your assumptions of like your residuals look at least approximately normally distributed, etc. So we'll just take a quick look at this data set. So this is from 4 individual model COD tracked as part of this. So these were, I can't actually remember the area this was in, besides it being green, but it's 4 individual COD tracked being followed by being followed by standard sort of positioning systems. For each observation, there's a date time. I've scaled it so I've got an index for each fish about how long it's been since that fish was first tagged as a way of measuring sort of dependence. There's Julian date, week, There's only 4 caught in here, so they're just individual tags. Long and ladder, self-explanatory. Then there's the depth of the fish, so what depth is currently at when it was observed. Then there's the bottom depth at that location. So, and I can use that to calculate later on here distance from bottom, so how far it is off the bottom. So cod are benthopelagic, and especially they spend a lot of time very near the bottom and will move up into the water column to forage, but they will very happily sit in the bottom and just hang out there. So it's typically more useful to model distance from the bottom rather than distance from the surface. Because if the bottom moves up, the cod will move up with it. Whereas if if the bottom moves down, the cod will tend to also move down with it. And then there's temperature indices at 6 different depths here. So estimated temperatures. And finally, I calculated speed in meters per minute. Basically, just use the X and Y coordinates divided by the length of time since the last coordinate. I'm sure I'm doing this incredibly, there are much more rigorous ways to do this. This is sort of a first ugly pass at estimating this. But this basically just gives you like the straight line speed from one observation to the next. Okay, where are we? So if we look at a histogram of, say, movement speed, there we go. So what we see is a very long tail distribution. So a lot of values concentrated very close to 0. Although I made sure that none of these values actually were 0. So there was, I think, 3 or 4 observations that were marked as 0 that I just added a very small amount to, because it doesn't make sense over these timescales for the cod not to have moved at all. And then you'll notice this has got but also characterized by this long tail. You're getting speeds per, meters per minute of like 40 up to 60 meters per minute. So this is the kind of classic data that you would not want to use the normal distribution for, at least if we plot against predictors, if our residuals looked like this as well, which they probably would, you're going to, if you try to model this as normally distributed, you're going to A, predict negative speeds a lot of the time, and B, wildly under-predict these high rates. But if we look at it log transformed, we actually get a wonderfully nice symmetric distribution. So these speeds are almost like, this is as close as you can get to like an ideal symmetric distribution when we log transform it, and which also pretty closely approximates what we expect from a gamma distribution. So this is basically telling me, and when I looked at this, this is basically telling me that, okay, this could probably be modeled pretty effectively with a gamma distribution, because it typically, when you log transform the gamma, it will typically have that like smooth, symmetric, hump-shaped distribution. And we could alternatively just log transform the speeds ourselves, but the issue is then we're making a model that's predicting log speed. We're not, or mean log speed. We're not making a model that's predicting mean speed. We're predicting the mean of the log, which can be very different numbers. So if we use the gamma, we're actually specifically predicting what the average speed is at a given point in time, but we're accounting for the fact that the data has this long tail. And this is a relatively simple model. So here I just want to see for each fish, how much does its speed vary over time? So I want to try and fit a smooth curve that says, okay, is it moving fast or slow? Is it a relatively constant rate of speed or like random variation? Or is there relatively predictable variation? So you'll notice here, I'm filtering the data. So I'm predicting just a specific cod. So I just want to look at one cod at a time. This is what Robert was talking about. So here I'm using the log link. So I use the inverse link. The plots that we see would actually be 1 over the speed, which is actually maybe meaningful, but not really that easily mentally driven. So often the gamma is kind of a special case where you actually want to say use link equals log. So you notice it's pretty fast to fit. And if I plot this, I get something that looks like this. So this is, just going to bring up a bigger plot. This is essentially showing that how the log of the mean is predicted to vary over time. So if you look at, say, and again, this has to be shifted up or down by the intercept. You'll notice this is centered around 0. So this isn't predicting, like, if you take e to this, it won't give you the speed. But if you add the intercept to this and take e to that, that'll give you the predicted average speed at a given point in time. So notice there's a pretty big variation between, kind of cyclic variation. We're seeing differences of e to the 0.5 is going to be around 1.5 times faster than one that's traveling at 0. And then e to the 0.5 is going to be about yeah, it would be like 0.75 or 0.65. So like, between here and here, there's a difference in average speed of about, the fish is traveling about roughly half as fast here as it is here. Estimated sort of over time. That's how we can think of interpreting these. Is you have to sort of mentally convert these curves back through the link to get predictions about the actual movement. So especially when you're dealing with this kind of data where it's like the default 10 basis functions here is probably not enough to deal with this kind of like high frequency variation. We know that speed is likely going up and down, maybe even on daily cycle or daily basis. But what we can do though is increase the number of basis functions to try and capture more of the variability. And this is a case where it's actually quite useful to increase the number of basis functions because we're trying to model a pretty complex function of time. So I do this and plot it. You'll still see that same basic curvy shape. We're now seeing much more, let's see if we can fix this issue. There we go. Yeah, you're seeing much more sort of like weekly variation. And it's still important to look at the confidence intervals and realize, okay, like you might be seeing these small fluctuations from day to day, but like the confidence intervals are telling you that there's other functions that are also consistent with this data. So like these tiny fluctuations from one day to the next might not actually represent a real increase in speed. It might represent just like, it happens to look somewhat bigger than that day. So you have to be cautious about trying to interpret individual bumps of these curves. But this still gives you maybe a decent view of like how average speed is varying from across the year. Yeah.
How would you interpret this in a biologically meaningful way? Like, are you seeing cycles that are associated with some environmental pattern, or is it just sucking up noise that's inherent?
I think this is probably just evidence that this is like, if you get like autocorrelated data, like speed is almost always going to be autocorrelated. Where like if it's traveling quickly one day, it's likely to keep traveling quickly for a while. Maybe just doing like a foraging trip or something. So this is likely just showing sort of shifts between active and maybe active and inactive states, or
kind of maybe see some seasonal trends as well.
I would want to, if I was going to look for seasonal trends, I'd probably look for like many more fish. So I'd use the full data set and try and fit like an annual trend. This is a good measure of seeing, okay, this individual fish shows a lot of variability. Let's just account for that dependency in the data. But this only is like one fish. It's really a sample size of one in terms of response to the year. So you probably want like say 50 or 60 fish to see if there actually is a seasonal cycle.
Fish is random.
Yeah. Yeah, assuming that the fish are independent of each other. It's a bold statement as well.
And I also wonder, like, with the plus type looks like, are you happy with the K value there? Or is it a little bit over?
So the K value, at least in this case, you're almost never going to have too large a K value. Like you can actually, actually it's kind of useful exercise to see what happens if I set, say, K equal to something truly insane. Try 150. So this is probably going to be a little bit more variable, depending on how autocorrelated it is, and it takes much longer to fit because there's 3 times the number of basis functions. So thank you. And might not fit at all. But it's probably going to show similar levels of variation to this one. Like, and you can check that. There's a function called check.k, because it's either check.gam or check.k, that will test to see whether or not you have enough basis functions for a given smooth. The general guidelines is to set your basis functions larger than you think you need to model a term, because the smoothness term will actually like get rid of excess variability. So you really just want to choose your basis functions based on, is there enough to vary, like, yeah. So yeah, okay, this is actually more, substantially more variable. So, you know, maybe you could justify even more basis functions here. But in general, like, you would set your k high. And like, in this case, it's actually not unreasonable to have a really high k here, because we do know that speed is going to be varying on like seasonal basis, on a daily basis, on a, you know, minutely basis. Yeah.
Would you fit the smoother on the daily basis in addition to the seasonal?
Yeah, so you could do that. So one thing I could expand, like if I wanted to try, like right now this is trying to fit time as like a single smooth. But what I could do here is say fit so I could add a term for week. So basically allowing like a term, you know, basically allowing the week of the year to determine it. And this is actually going to be collinear because there's only 1 year of data here. So I might. But you know, if you had say data that spanned multiple years, you could actually have for a single fish like a weekly term and say you know, an interannual term like where the mean speed might vary from 1 year to the next. Yeah, that kind of variation you could break it down. You could actually like decompose it into different time scales.
Yeah, and in the fish we often see like a flow pattern where they're active at day and inactive at night. You capture that in a smoother.
Exactly. Yeah.
Going from 0 to 24.
Yeah. So like, this is. Yeah. So this is giving a terrible answer because like week is collinear, very collinear with time. But yeah, you can at least see the idea that we could actually have like a cyclical week term. With the flu data, for instance, you could have that week term plus a year term plus a, you know, so on and so forth. I'll quickly just touch on the distance from bottom example, just because it is a handy one as well. Because this is this kind of data that's continuous, but also has a bunch of zeros. So we can't model as normal distribution, we can't model as gamma, because gamma can't handle the zeros. So basically this COD, about 30% of the observations here are on the bottom. Or actually got coded as negative because the sensor had enough error on it that was predicting that the COD was beneath the bottom. We can actually look at what the fraction is. Yeah, it's about 30% of the observations are zero. So it's a pretty large fraction of the time this COD is just sitting on the bottom of the ocean, or very close to the bottom of the ocean. So what we can do then is actually model this with a Tweedy family. So here, so I'm just, rather than modeling as a function of time, I'm going to look for a term of weekly variation. And then this is just the individual clods. This is looking at like a random effect to see if the mean distance from bottom to these clods vary. If I do this, I'm actually going to do this as age equals 1, because it's annoying to look at. Yeah. So this is saying for the 4 COD we've measured, we have our variation in distance from bottom across the week. So basically it's saying that there's a bit of a shift from COD that spend most of the time further above the bottom at the start of the year. So this week would correspond to early winter. And then you notice they get much closer to the bottom in they get closer to the bottom in the summer, summer months and fall months. Again, this is only based on 4 COD, so this is probably a wildly optimistic prediction of how this actually varies, but it does give you a sense of how you could estimate something like, say, distance from bottom as a function of time, and how you can actually take into account the shape of the data when you're modeling it. So using this Tweedy distribution. And the last example I want to walk through in this section is just this Panther data. So this is data that I got from a book by Robert Fletcher and Marie-José Fortin called Conservation and Ecological Modeling, Spatial Modeling in R. The reference is in the, I'll post the reference in the paper afterwards. Just give you a sense of what it looks like. This is data used for step selection, so it's panthers from Florida. That's not what I wanted. It's 6 panthers from Florida that were tracked using radio collars. So this is roughly daily observations, maybe a little bit less. And you can see where each panther is observed. So each line represents one panther. You see the kind of habitats they're moving through. So a problem for this might be, okay, what kind of habitats does this panther prefer? We also could look at and say, okay, these panthers don't seem to be moving very far away from a core area, so maybe there's home range-like behavior. So maybe these individual panthers are actually moving back towards like a center of activity. So we might want to know, okay, do they prefer different habitat types? So here if I get rid of this, yeah, so this dark green, for instance, corresponds to hardwood, and we see some scrub forest here. So they seem to be spending a fair bit of time in hardwood and scrub. We might want to quantify that. Like, do they actually prefer hardwood over other types of movements? Can we statistically quantify that preference? And we might want to also look at, okay, what's the probability of them taking steps of a given size? Like, are they likely to take short or long steps in this given period of time? So what we can do here is, so first load the data. So I'm recoding habitat and cat ID as a factor, just because, again, MGCD has to have them as factors. This is the actual plot of just the steps for each individual and the alternative steps I made. So what I did is for each step, like each potential step they took, I generated a compass rose of 8 steps around it, times 4 different distances. So basically, it's like, you can think of it like stacked compass roses going out from the center. And then for those I actually randomly just rotated the steps and also squeezed them in a bit for different cats. So I'm trying to get a sense, I'm trying to sample the possible turn angles and the possible step lengths they could have taken when they made this movement. So this is like the alternative steps for each cat on the left. These are the actual steps. You kind of get a sense for like what range of data I'm giving it as alternate values. And hopefully you'll notice that like the ranges for the alternative steps are much bigger. They span much more space than the actual observations. So one thing I could do in this model is I could, for instance, trade a null model. I might say, okay, I just want to fit a standard random walk model to this. I just want to know what's the step length distribution and the turn angle distribution for this. And this is actually something that's very difficult to do in a standard step selection model, because you have to assume linearity. In fact, the general advice for standard step selection models is actually like, when you create your proposals, you should draw them from the distribution of step lengths and turn angles of the data itself, because it's pretty hard to estimate it otherwise. You just might end up with not a good match. But here I can actually use a smooth function to estimate which step lengths they prefer. Do they prefer to move a certain like short lengths or long lengths compared to the possible options? Few sort of key things here. I created this times variable. So this C-bind is our code. This is actually 2 columns. Times is going to be it's just a single one. So in a standard survival model, this would correspond to how long you've observed a person or animal before they passed on. Here we're just assuming we've observed everything for the same length of time. So time is 1. Then the step stratum corresponds to which step they correspond to. So you've got, for each step, you've got 32 alternative steps, and you've got 1 step. And each of those are classified into a stratum, like we were talking about before. We have our smooth terms. And then finally, we have the weight. So weight corresponds to, this is how GAM specifies whether something is an event or not. So here, 0 corresponds to an alternate, so it's not the step that was taken. And then 1 corresponds to the actual step. So this is trying to fit a model comparing which steps they took relative to what they could have taken. So given this is roughly 20,000 observations, and the Cox model is pretty complicated, this fits actually relatively quickly. It should be done in a couple seconds. While it's doing, we can do a quick summary of it, and we can see that, okay, so there's both these terms are significant. Just them being significant doesn't tell us that much, but we actually look at the plot of this term. What we get are now nonlinear but interpretable functions that tell us the preference for this cats for different types of movement. So this is relative to the zero line. It tells us whether a given category is preferred or not. So there's no intercept in this model. So the Cox proportional hazard doesn't have an intercept at all. So you can interpret the terms as like any negative values here correspond to characteristics that are less preferred than average. Positive values correspond to more preferred. So we can see as the cats aren't taking nearly as many steps of length, say 10 meters or 100 meters, compared to lengths of say 1,000 meters up to around 10,000 meters. So at the scale we measured this cat at, most of the steps are this like 1,000 meter length. So they're moving about a kilometer per step on average, and maybe a bit more. We also see that there's a strong preference for turn angles that are far away from zero. So normally we'd expect with a random walk, the turn angle is concentrated around zero, but like most of the time they're moving like only doing a small relative turn. With this case, we're actually seeing that the cat is most frequently exactly reversing the direction from its last step. So if it stepped 60 degrees in one way, the next step, more often than not, is actually turning around and going back, which is a pretty good indication of home range seeking behavior. If it didn't have that behavior, if it kept, it kept the same turn angle, we expect the cat to eventually diverge off to infinity. In this case, it actually keeps moving back to where it was. So this basic model already tells us something about the movement behavior of this cat, and it allows us to fit it without having to specify a distribution of step lengths or a distribution of turn angles. And then we can add a simple, sorry, I keep using the word simple when I realize this is overly complicated. But I can add a random effect that basically says, okay, I want habitat type to vary. I want to allowed to choose which habitat types it prefers. And I'm putting a random effect in that because I want to penalize them towards it. I don't want them all fit independently. There's too many habitat categories to get a good estimate, so I penalize them towards each other. The summary and the plots aren't that actually informative, but what I can do is actually create predictions for it. So I can create data that looks at different possible habitats, set the step length to fixed. Then I can use the predict function here. Let me just run this. So I didn't actually run the habitat pref, but it would help. I can look at the predictions from it to see if a given habitat type is preferred or not relative to others. So we try and say, okay, is dry forest preferred to wet forest or whatever? So if I look at this, that's the problem. So what I can see is that, okay, any positive values here correspond to a habitat that's preferred. So one that they tend to move into when given an option of all the other habitats. And bigger values correspond to ones that are more preferred. So a really big value corresponds to a habitat that they'll move into as much as they can given other habitat types. So you can see they're preferring coastal wetlands, hardwood, and dry prairie. And then if they're given a choice of, say, scrub versus grassland, if all they have is scrub versus grassland, they're probably going to choose scrub, because scrub is a less negative value. So this allows us to see which habitat types are they preferentially moving into, while still taking into account that turn angle and step distribution. And this continues on. I'm not actually going to dig into that because that's getting overly complicated. And I realize that survival data analysis is going to be handled tomorrow, so I don't want to steal too much thunder from that. But I did think this is a useful example to show what GAM can do. I'm going to pause here and ask what questions people have. Yeah?
Just coming back to the random effects.
Yeah.
If we have like a data set with multiple coefficients, we want to account for zero variables. Is there any difference using like a random effects smooth or using a generalized additive model?
So if it has the same family and you're using Dremel for both, you get essentially the same estimates. It's doing the same thing behind the scenes. They're specified a bit differently, but they're not going to get different estimates. Welcome. Just seeing if there's any questions in chat. Okay. Okay. How are we doing for time? I didn't actually notice what time we're. I'll give it another I'll go for another just 15 minutes, just so we did go to 3:45, and I'll go quickly through the last parts. Computational time, important to know about. There are tricks to deal with it, but you can go through the slides. I don't think me walking through them is actually that useful right now. Besides the fact that if you're running the computational time and you're dealing with complex movement data, think about subsampling your data. Most of the time, if you have data at the resolution of say seconds or minutes, you don't need that much data to fit the smooths you're trying to fit. If you're trying to fit a relationship between say temperature or say temperature and depth at an annual level, you don't need millisecond or second or even hourly data to fit that. Subsampling is there's nothing wrong with throwing out data when it would take too long to fit, and you don't actually care about that level of fine scale precision. I know it feels bad to carefully collect this data, but it's perfectly acceptable to drop data when needed. So this is one of the bigger issues, is the statistical dependency, where if you've got many observations in close succession, the issue is that these measurements are more related than you'd expect otherwise. We didn't randomly select these points that we observed for an animal. They're dependent on each other. And that can lead to a couple of major problems. So first it means is that your standard errors for your model, like any model, are going to be much bigger than they would be otherwise. Or sorry, your standard errors should be smaller than they should be, and your smooths will be more wiggly. So basically it's going to try and fit very wiggly smooths because your data, it thinks you've got more independent data than you do. The second one is that, if your covariance very slowly, so say a fish is moving along a depth gradient, it's not changing depth quickly, or the temperature is not changing quickly, you could run into issues where you can't tell if the variation is due to just the variation, the daily variation of the fish itself, or the variation is due to temperature affecting its behavior. And it's this issue of dependence, and it's this issue of collinearity. Is that we don't know if a fish went from a low to a high temperature gradient in a day just because it happened to want to go on a foraging trip, or because the temperature is different by half a degree. We don't know a priori which is which, and we can't necessarily tell them apart just through observational data. And I hate to say that there's actually no solution to this. This multicollinearity issue is not one that's solvable, short of knowing what the actual causal factors that are driving your fish are, and ideally having data that's well enough separated that is relatively statistically independent. So we're never actually going to get away from the point of where we have to deal with collinearity. Basic options are again for subsampling. So one thing that can work is actually cross-validation as well. So rather than throwing out data, you can actually break your data into say 100 bins that are at hourly timescales instead of say minutely timescales, and then fit your models for each of those bins and average across models. So if your data is effectively correlated at the second-to-second scale, but it's not correlated at say the minute-to-minute scale, or it's not correlated to the hour-to-hour scale, you can subsample your data and then fit the model multiple times. You can also add a smoother to model the temporal dependency or spatial dependency itself. We saw that with the COD movement model. Where I was adding that smooth, that's actually accounting for the autocorrelation in movement rate. It explicitly models dependency. This is the same way that in a GLM, or sorry, a NLME, for instance, you'd add a spatial covariance term or a temporal covariance term. Adding a spatial or temporal smoother is doing the same thing. It's trying to account for that dependency. The downside is it assumes that you've got the correct specification for that dependency, and it can be slow, and it can also lead to fixed effects disappearing because of this collinearity. This is if you run into this problem where you've got a really strong relationship between, say, temperature and depth, and then you add in a term like a smoother to try and account for the spatial correlation, or you add in a correlation matrix, and you find that really strong term you loved vanished. This is a good paper to read about why that can happen and how you might be able to deal with it. The other thing, this is one's a little bit more experimental, is if you can also adapt the effective sample size. So you can basically tell MGCD that each sample point should count for less than they are, or should count for a smaller number of samples. And there's an example in the script, we won't go through because of time constraints again, but there is an example in the script that shows about how you can deal with this with the step selection case. Because there we don't have like 32 independent observations for each step. We have one independent observation for each step and 32 pseudo points. So what we can do is basically just divide our sample size by 32, and we get much more effective, like much more appropriate standard errors. In the interest of time, I do know that people are probably most excited about this idea of interaction, so I'm going to quickly just go through these slides before doing any more work on the script. So one of the things you might most often want to model is something like spatial variation. So say you want to model is an individual moving more quickly in different locations. We can't just model this with, say, one linear term for longitude, or one nonlinear term for longitude, one nonlinear term for latitude. We actually have to model as explicit interaction. So you look at, say, the coast of Newfoundland here. We can see that shrimp have high density in this mid-shore range and have low density in this region. There's no sort of like single one-dimensional smoother we could fit that would capture this. We need to explicitly model this variation in biomass with both. So one thing we can do is if you just use this S term and give it a second variable, it's actually equivalent to, it's fitting a multi-dimensional smoother, but still only has a single smoothing parameter. So it assumes that like, it's what's called isotropic, so it assumes that like it's equally smooth, like the function varies equally smoothly in like the latitude, longitude direction, or in like east-west direction, so we don't expect to see big swings in one direction or the other. So if you've got cases like X and Y coordinates where they're in the same units, you basically want to use this approach if you have things that are measured in the same units. So X and Y coordinates that are in, say, UTM coordinates, this is a great one to do it for. If you have, say, temperature and depth, it doesn't work well. If you've got longitude and latitude and you're far away from the equator, you again don't want to use this approach because longitude and latitude aren't measured in the same units at that scale. So there's not going to be varying at the same level. Just to show you what this looks like as we change how this varies. So this is a model for this. So it's just a model of 100 basis functions with X and Y as our axes, and just a 2,000 trials for a single year plotted here. I'm going to show you, so we're going to see more about the Gradia next time, but this Gradia is a package for drawing GAMs, and it produces much better two-dimensional visualizations. So, yep.
There's a question from Maurizio.
Yep. Yep, go ahead.
Thank you. My question is about the units. Till now, I always use the same units. For example, the Celsius degrees and Celsius degrees, or meters and meters, or geographic degrees and geographic degrees. But for example, in case I use a probe that collect in parallel different measures, but they have the same, for example, the same peak, for example, or the same time record. Are they? Is possible to put them with the same spline or no?
So if I'm understanding right, yes, you can have interactions where things are measured in different units. You just need to use a different type of smoother that takes into account the fact that things might be more variable in one dimension than the other. I will talk about that actually in a second.
Okay, thank you.
Welcome. Interpretation of this is basically showing like where we have large or small biomass. So we can just see this picking up 3 hot spots of biomass which correspond to some of the biggest areas for fishing for this spot. So the smoother is able to quickly capture where we're seeing hot and cold spots for shrimp biomass relative to the average biomass in the system. It also is giving you isoclines that show how biomass is varying away from these peaks. So red areas are going to correspond to high biomass, blue areas correspond to low. You'll also notice the smoother automatically, the plot automatically excludes areas that are too far from your observations. So I didn't have any observations here, so the model's not trying to predict to those points.
So it's not like you didn't overlay a shapefile, it just happens to identify that outside of the water.
Yeah, basically it looks at the range of your observations and like make sure it's not predicting too far in like a linear direction away from those.
We'll be touching on soap films.
What was that?
And on the soaps.
We won't be touching on soap films, but this would be a good example of where you could use it, where you could actually have a smoother that goes to zero at, at the shore. Or this one also has a natural line of say, there's a sharp drop in depth there. So you could actually have another smoother that says goes to zero there.
So you would have the soap in addition to this with the.
You would model it with you would use the soap instead of the thin plate. Okay. The other multidimensional smooths that are useful to know are these thin plate ones. So this basic, saying S, X, Y, just telling it whichever covariates you want to add to the interactions, doesn't always work. So like a covariate can easily be something varying much more quickly in one dimension of your thing of your data than another. You want to look at interaction. So if you want to use, say, lat long, or if you want to use, like, say, depth and temperature to measure something as a function of how speed is changing, temperature and depth aren't even measured in remotely the same units, so we don't expect them to have similar smoothness. So here we actually use what are another type. So instead of using S, we just use this term called TE. It stands for Tensor Product. Again, overly complicated term, basically just means it's multiplying the two smooths together, and it lets them be differently smooth in different directions. So we just swap into the GAN for the shrimp GAN here. We're swapping in TE, we're modeling now, say, depth and temperature at bottom. We're modeling biomass as a function of these two. And if we look at the plot for it, well, I thought I had a plot in there, but yeah, so you can actually see what at least we can see the smooth term here is, getting an effective degrees of freedom of 15. So basically there's 15 independent basis functions here. I'll actually go back to the slides after this and add the plot in just so you have to look at for your own notes. But yeah, the basic idea is it will look something similar to the map, except it'll actually have it'll allow for more variability in one direction. You notice here, if you go, say, in the X direction, things are changing at about the same rate as they are north and south. Like it's changing a little bit more quickly north and south than it is, sorry, it's changing a little more quickly east and west than it is north and south, but they're relatively comparable. But if that was not the case, so there's actually, say, a gradient where things are changing really quickly in this direction, we'd want to use, say, something like a thin plate spline tensor product to model that. Okay, the last thing we want to talk about is just this concept of individual variation. So these tensor products, so these combinations of smoothers, are exactly how we can use to model individual variation. So we want to model how two individuals have different functional responses. We can do it by basically creating an interaction between a random effect that codes for our individuals. So each individual would have a random effect, and whatever smooth you want to measure to model the individual relationship with. So because we're multiplying the two, what you end up is getting a separate curve that's fit independently for each individual. But they are models that will have the same relative level of smoothness. And just to kind of sketch out what that looks like, so I have a pen here. So if we have like one individual, so this is, say, depth versus speed. We might have one individual that looks like this. We might have a second individual that looks like this. We We have a third individual that looks like this. So each of these represents sort of a relationship of movement speed versus depth for a different individual. So here we're saying that each individual has its own functional shape, but they're all equally smooth to each other. So they're not one's not changing more quickly than the others. And this is really that's the heart of this concept. The HCAM is allowing for each individual or each level of some group to have its own separate function that you're trying to estimate separately.
It isn't just.
Yeah. Sorry.
Oh, so you're referring to it in the next line.
Yeah. Yeah. So that's. See, this will actually advance. I might just quickly reload this. I never learned not to build these slides in Markdown rather than just making a PowerPoint like I should. Actually, this is probably a good point to pause anyway. I think we're already at our 5:15 level and the computer wants to take a break, and I suspect you all want to take a break as well. There are more slides on that talking about the different options for hierarchical GAMs. So you can have either ones where individuals' rates of change vary more quickly. So some individuals have less smooth or more smooth terms. And you can also have HGAMs where there's an overall term and then individuals vary around that term. So this might be the case where you're saying, okay, there's an average relationship between, say, temperature and speed. So across, say, all cod, we expect to see an average relationship between temperature and speed, but an individual cod might have variation around that. And we might want to quantify that individual level of variation as opposed to just quantifying that average relationship. So we can do this by having a model that has both a mean function and a curve for each individual cod. And we're also working on, this is work we're ongoing, but I have a PhD student currently working on taking into account not only, so these can only allow for like each species to have its own curve. What we're trying to do now is actually take into account functional relation information as well as phylogenetic information to see if, say, do, say, cod and, or say, perch and perch pike have similar temperature relationships or close relationships to each other compared to, say, largemouth bass. So we want to see if, okay, species that are phylogenetically close to each other have more similar functional relationships to each other. So keep an eye out for that. We're working on it right now, but the idea is basically trying to see if we can use phylogenetic information and functional information to penalize species that are close to each other in traits or in phylogeny to have more similarly shaped functions. So keep an eye out for it, hopefully in the next few years. And I think this is probably a good place to stop. There's more code for you to go through, but I think it's much too hot in this room to continue on or in front of the laptop. But I'm happy to take any questions. Thank you for your attention. Any questions going on online? Oh, perfect. Okay.
Here.
Okay.
Is there any sort of post-hoc test in GAMs that you do? For instance, if you have a treatment which, say, 3 or 4 different levels, it's having an effect on, let's say, basically, can you?
So you're talking about the post-hoc testing in the sense of like trying to distinguish like. Yeah. So the penalization is really doing the same job as the post-hoc testing. Like with post-hoc testing, the idea is, okay, we've got a bunch of independently estimated levels. Given that we've estimated 50 of them, do we have evidence that these two ones differ from each other? So what GAMs do instead, or what the philosophy behind mixed effect models in general, is that rather than trying to increase the width of the confidence intervals, which is what a post hoc test does to evaluate are they significantly different. What it instead does is says, okay, we're going to pull these estimates towards each other. Oh, yeah. Thank you. I guess it's not good for me to just look at this. We'll try this again.
You got a different kinds of boards here, but it will be recorded.
Oh, yeah. Hey, that would show up on the screen here, though, wouldn't it? Yeah. Yeah, so let's try it on them. So the idea for a post hoc test is we say we estimate like 3 levels. We have a, we've got like a naive, sort of a standard error for them, right? And we're trying to tell are these two different from each other. So what a post hoc test does is actually effectively increase the size of those confidence intervals when making the comparison to take into account the number of comparisons you do. What hierarchical models do is instead it actually pulls the estimates themselves towards each other. So it's saying that, okay, given that we know that these estimates vary, and we have information on the fact that they're all drawn from a similar population, it pulls them towards each other so they're a little bit closer. So generally you can do like direct comparisons of differences. You could do direct comparisons of differences between treatments within multi-level, within a regression, because it's already accounting for that, the fact that you fit like 4 coefficients or 5 coefficients by pulling them towards each other. And Andrew Gelman talks about this a fair bit in his hierarchical models and regression and other stories. They've got Andrew Gelman and Jennifer Hill have a good discussion about that there. Oh yeah.
Okay, I can turn it off again.
There was a question from someone online.
Yes, mommy too.
Okay. Go ahead, Mauricio.
Again, maybe this question may go quite far from the specific lecture, but I was stimulated about, for example, since we faced now latitude and longitude coverage, I was imagining a scenario like working with rasters. And I imagine to make statistical analysis with the rasters. So in case we use rasters as you, should we like make a kind of brick of all raster that we want to study, or we don't need this kind of passage?
I'm probably not the right person to ask about raster information. I've used them a little bit, but I can't tell you enough about like the ins and outs of like do's and don'ts of downsampling or upsampling raster data. It's just not one I've worked with that much myself.
Okay, thank you.
Welcome.
I appreciate your answer anyway. And then I have another thing. For example, in imagine to work with species in which in some days you don't have like sightings or data, so you have 0 about, for example, the species that is of your interest. How can we deal with the absence or pseudo absence?
I mean, where you just never observe a species at all?
No. For example, I have day 1. I have depth, temperature, of course, coordinate, and for example, a number or a value of abundance. Day 2 also, day 3 also, day 4. I have everything, but not. I don't have an encounter with the specimen. Day 5, I have another time encounter.
So if it's a case of you're just like looking at the given behavior, I think in that case you would just like remove any data points where you don't have encounters, unless it's actually like, maybe I'm misunderstanding. I'm picturing it as like you're trying to see if the behavior change of say temperature. If you don't have any like evidence of behavior, you just exclude that data from the
okay, so
if it's a case of like, so yeah, sorry, go ahead.
But for example, can be also a howl in which you usually harvest a species like cod, but one day in one specific howl you don't find the cods. So you just remove that day of survey from the dataset, and you work with it, like with presence only.
Yeah, there's always issues with like dealing with missing data, but it's not really, unfortunately, I'm not really enough of an expert on the sort of missing data side of things to give you much good advice on that either.
You're just bragging.
What's that?
Now you're just bragging.
Okay. Thank you.
Yeah.
So if you model the latitude, longitude, and for each position you have a given error, estimated error, would it be more correct, you think, to model the latitude and longitude with interactions of their error, or would you just add the error as an additional variable?
Oh, as the, like we got measurement error on your X and Y.
Yeah, so for each X and Y you have an error.
So that kind of errors and variables problem is actually, it's one thing that is very tricky to handle with a GAM, because you have to think about like it's not just your observations that are varying, it's like the implied non-linear functions.
Because it rolls over.
Yeah, and I've thought about it, I don't know a good way to directly incorporate measurement error in your X's into, like in your locations.
I'm assuming there must be a better way than just filtering out.
Yeah.
Right.
Yeah, I mean.
So what if you add the error as an additional variable, like you smooth the error as well?
Yeah, so you might be able to like take a bunch of samples from like the possible region and like treat those as if like a bunch of observations, and then just downscale, basically use gamma to divide by the number of extra observations you have. I don't know if it's going to work out.
So it's like that one thing, right? Because there's an error and an error.
Yeah, I'm not. I thought about it for a while, and I can't give you a better answer, but I don't know if there is an answer or not. All right. Well, I think it's a good time to call it here. So thank you very much, everyone.
So,
Eric, indeed, thank you very much for a wonderful afternoon.
With very minimal HGAM coverage.
Okay, guys, see you tomorrow morning. It's 9 again. And enjoy your evening.
No party today? No party tomorrow today?
So hot.
It's now or